Hi, so welcome to our video series on basically basics of mechanics. So here what we're going to do is talk about moment of inertia. It's going to be both mass moment of inertia as well as area moment of inertia, and we're going to look at buckling. So first we'll kind of quickly recollect what torque and moment are, and then we'll think about what buckling and how it relates to the area moment of inertia, bending and how it relates to area moment of inertia. Then we'll talk about buckling, and then finally we'll talk about rotation and mass moment of inertia. So generally, if you take a look at a force, if the force is acting at a particular distance. So if I have this pen over here, I'm holding it at this point. So if I apply a force like so, it's not going to be, there isn't going to be any rotation. But instead, if my force is basically offset, so instead of the support, I'm going to move the force over here. And then if I apply the force, the object tends to rotate. So if I'm clever enough, I'll rotate my fingers over here and then kind of apply a balancing force. So you can try this. What you're essentially doing is you're applying a kind of a counteract to this force at a particular distance. This counteraction is known as the moment. So generally what happens is if I'm not counteracting, we measure this and call it the torque because it's going to cause an angular acceleration. So essentially this is going to get faster. And if I'm using in statics or dealing in statics, I'm actually trying to resist this force at a particular distance. So we tend to call it as a moment or a bending moment. So these are kind of conceptually the same thing, but basically what happens is the units are still the same. So the units are going to be a force times a distance. So the unit is going to be Newton meter. The actual torque is actually a vector. So you need to keep this in mind. So the magnitude is actually Ft sine theta. Basically T or M is going to be D cross F. So D is the position vector. So that basically is going to be measured from our origin. So this is going to be my D vector, like so. And then this is my F vector. Right now this angle is 90 degrees. So this sine theta term becomes 1. But this cross product here is actually valid for all forces and positions. So I can basically do a force and then try to find it about another point. So the same force, I can actually calculate what's the bending moment about this point. So essentially what I need to do is I can take this and then take it to any point on this force. Then this angle becomes theta. And then if I do this, notice that basically the right hand thumb rule basically says this R or the D is like so. The F is in this direction. So basically if you have the right hand thumb rule, it's going to be coming out of the sheet of paper. So typically you could use kind of an arrow pointing out like so. So the next thing is when this bending moment is basically resisted by a structure. So I have like this, I'm kind of like really holding it down. So then there is going to be a bending moment. So this is not actually rotating freely like so, like this, but it's going to be bending. So if there is a weak spot, for instance, there's a weak spot over here. So I bend it, it's going to kind of bend more at this particular point, excuse me. So as before, the force or the moment and torque are still force acting at a distance. So I can take a little area. So we pick an axis known as a neutral axis, which is basically kind of like a zero reference. And then if I pick this particular point over here, and then notice that somehow I'm able to figure out what the stress is at this point. What I'm going to do is take a really, really small area or an infinitesimally small area around this point. So the force acting at that point is going to be the stress times this infinitesimally small area over here. This is going to be the force here. Notice that this point is at a distance y from our reference axis. So this is my axis of rotation. So basically what I do is I need to multiply this by y. This gives me the small moment. So this will be my d m. So d is the kind of used to denote like a differential or an infinitesimally small value. So now if I want to calculate the total moment about this particular axis, then what I need to do is kind of integrate this term over here. So my total moment m basically becomes integral, and then it's going to be sigma dA times y. So now in the case of bending, there is a special axis known as the neutral axis. So when you kind of measure the stress above the neutral axis, there is a formula that the stress is actually proportional to the distance from the neutral axis. So this is neutral axis, so if you get further and further away, the stress becomes larger. So what we basically say is, you know what, I'm going to just call it as sigma is some k, which is some constant, and then times y. Right? This is only valid when you're measuring it from the neutral axis. So what can I do? So I'm going to put this over here. So what that basically does is my m basically becomes, and then I can pull this k outside, so this basically becomes k, and then you have the integral, so this is over the area of the surface. So I have one y from here, and then I have another y over here. So what basically happens is this becomes y squared, and then we still have this dA, right? So now my my m is some constant times y squared dA. So this term is kind of like a completely structural term. So this we denote it by the letter I, which is the area moment of inertia. Moment of inertia. Right? So now what I do is kind of call, and then we call this as I. So this basically means my k, which I kind of defined before, is actually m divided by I, and then what I can do is take this and substitute it over here. So that basically means my sigma becomes my by I. Right. So this is a standard bending stress equation you would have basically learned all over the place. Right. So this is the standard bending equation that we basically know and love. So now we're going to look at buckling. So buckling is actually a structural instability. So imagine you have this particular beam over here. I'm going to apply two forces, like P, like both are compressive, so they're kind of going towards the center. And then if I do that, what's going to happen is that the object itself is going to kind of deform, kind of move like so, and then arrive at this particular shape. So question is, why does this actually happen? So to examine that, we're going to use our friend static equilibrium and free body diagram. So imagine I'm going to cut this particular beam at this location over like so. And then when I do that, I can look at this one section over here. So now this still is P, and then I need to apply the same P, otherwise this beam is going to run away. It's going to kind of like run away so. And let's imagine that this distance is some W. So now what do we have? So we have two forces, they're separated by a distance W. So essentially, if I don't apply any moment here, this beam is going to want to do kind of like this. It's just going to keep going in circles. So what I need to do is apply a moment over here. So if I want to avoid this, if I don't want to do this, I have to apply a moment, which is basically m is this P times W. So if you recall from your statics and beam analysis, you notice that anytime you apply a moment, the moment actually causes a deflection. So right now this moment is here. So imagine I have a beam like this, and then if I apply a moment like this, this actually would cause a deflection as well, right? So this is actually kind of like a fixed thing condition. But anyway, so what happens is the geometry is such that the deflection, if I just apply a moment over here, it's going to produce a deflection in this direction. So what happens is when I apply a moment, for a small, even for a small deflection, the beam is going to experience a small moment. This moment, because it's acting to increase the deflection, what happens is the deflection becomes a little bit larger, right? So the next step is, because the deflection is larger, the distance between these two P's become larger, my moment increases. So I get a little bit larger moment. So because the moment is larger, my deflection becomes larger, moment becomes even larger, and then both of them keep increasing, and there is actually no stopping of this. So this is actually more of a runaway effect or a positive feedback. The only time this actually is going to stop is when your structure actually breaks. So if it's a metal, it's going to break. If it's like plastic or something, it's going to yield. So the long story short is that we don't actually want this happening. And from statics and more analysis, they've actually found that this buckling is actually a function of this force as well as the structural property and the elastic modulus. So because it's kind of like a bending related equation, we basically have this EI term that shows up, which is basically E is the Young's modulus, I is the area moment of inertia, L is the length of the rod. So essentially, if you have a smaller rod, if it tries to deflect, it isn't going to deflect too much. If you have a longer rod, it can kind of potentially deflect more. So that's the reason you have the length coming up over here. And then finally, you have this column effective factor. So this kind of basically measures what is the effective length. So essentially, if it's free like so, then the value of K is 1. So this is a simply supported. So this K becomes 1. If you have a different shape, so for instance, if it's fixed at both ends, and then for some reason it's deflecting, so what will happen is the deflection kind of becomes like this. So we need to kind of figure out an equivalent length, which is going to be this distance. So this K helps you kind of relate from here to here, right? So we're not going to worry about it too much. For our analysis with trusses, K is always going to be 1 when you're doing truss analysis. And more importantly, when you're doing a truss analysis, any truss section which is actually in compression needs to be evaluated for buckling. So it's really important that we do that in our designs. So the next thing we're going to do is actually look at rotation.